So this implies, because by the properties of the function mean stated above, the summation of m mean Rk is different from 0 and thus equal to 1. Only if n is equals to 1, example, is equals to n, in particular for f1 is equals to 1 and fn is equals to 0, n is equals to 2, 3, and so on. Theorem 6 implies that there exists precisely one function f, namely the Mobius function, mean n is equals to fn, for which the following conditions are satisfied. Liouville function. This is the arithmetical function defined by the conditions, provided the factorization of n into prime numbers is of the form 1. We have 1 is equals to 1, 2 is equals to 3 equals to negative 1, and 4 is equals to 1, 5 is equals to negative 1, 6 is negative 1, and 7 is equals to 8 minus negative 1, and 9 is equals to 10 minus 1. Suppose that for a natural number n is greater than 1, the factorization of n into primes is as in 1. Consider the product, this formula, where is an arbitrary integer. Expanding this product, we obtain the algebraic sum of the summands, each multiplied by negative 1 to the power of 1 plus and so on plus 2k is equals to q sub 1 to the power of 1 and q sub to the power of 2 and so on, q sub k to the power of k, where the summation is all over the set of the divisors. G is equals to q sub 1 to the power of 1 and q sub 2 to the power of 2 and so on, q sub k to the power of k of number n. Consequently, the product is equal to the summation of d times d to the power of 3. On the other hand, the formula for the sum of geometric progression gives this one. And applying this to each of the factors of the product, we get, in particular, for 8 is equals to 0, we obtain the formula. And the number 1 times negative 1 to the power of a divided by 2 is equal to 0 or to 1, depending on whether or a is odd or even. It follows that the left-hand side of formula 40 is different from 0 and thus equal to 1. If and only if all the exponents a sub 1, a sub 2, and so on a sub 8 are even. Example, if n is the square of a natural number, thus we have proved the following. Theorem 7. The sum of summation d is equal to either to 0 or, in the case where n is the square of the natural number, to 1. Although, in the proof of Theorem 7, we assume n is greater than 1, the theorem is true for n is equals to 1 since 1 is equals to 1. Let fn is equals to the summation of d. Consequently, fn is equals to 1 holds for any n, which is the square of natural numbers, and fn is equals to 0 otherwise. In virtue of 30, for fk is equals to k, we obtain this formula. Whenever x is greater than or equals to 1, the sum on the right-hand side of this equality consists of as many summands equal to 1 as there are natural numbers, that is, greater than or equal to x, which are squares. Consequently, the sum is equal to the square root of infinity